I am now starting our recording. So welcome. It's Design 330. It's our lab. We are going to collaborate today by doing a design review. That's the portion that we're doing. And I am recording this session. So that's not right. I am recording the session. I think it'll be useful for others to see a design review in process. Okay, so what I'd like to do is have everybody go ahead and access in. I see Michelle is in right now. If you can, maybe I'd better put this. Maybe I'd better put this in the chat. So here we go. So I just put the link to the Jamboard in the chat so that you can click on it and go to it. And we'll get as many people in as we can. There we go. I see everybody showing up here. That's really cool. And then remember to put your name on here if it's not already on here. This is where we'll record who gave input. And for those of you who are not here right now, but will be watching this recording, you're welcome to come in afterwards and put your name in here and add some substantive information of your own that will show that even though you weren't here, you can follow how we're doing things. All right. So it's okay if people are not here. So hopefully, Alex, let me put the, I think you might have got in after I put that in.
Yeah, sorry I'm
There
late,
we go.
guys.
Yeah, no problem at all. I just put the link in again so that you can get to it. There we go.
Perfect. That was my first
Yes,
question.
like how do I get in there? um, so there we go. So go ahead and make sure that you put your name on here again. You can use the sticky notes. That's an easy way to do it. If you want to write text, you can do that. If as you're talking you need to show something, there's a laser down here and you can just circle anything that you want to be able to circle. Here's the pointer tool if you need to highlight and select something. We'll try to stay away from the eraser tool unless we really need to. And then here is the different pens, and you can use different colors if you're trying to do something. So here's what we're going to do. We're going to step through each page. I've added some questions that I'd like us to discuss and hopefully have some substantive information. And if you've got, it's hard to, they don't just let you put a snip on here, which is kind of too bad. But if you have some information, you can either add an image or make a sticky note or just type something if you have some specific information to do. All right, so the first thing that I'm going to do is, okay, well, this is a very good one right here. I was thinking about that one just a few minutes ago. But the first one I want to do is ask, how much water are we going to need to pump? That's our first functionality question. So somebody go ahead and put down some tabs or some notes. Everybody can just put something in. How much water do we need to pump and how fast are we going to do it? Are we going to need a teaspoon, a cubic inch, a gallon? So a few of you go ahead and please put down what based on your information from the types of tests that are going to be run. And you could even say for a pH test, we need 1 cubic inch. For a COD test, we need 6 cubic inches. For this test, for that test. So if you guys can just go ahead and pop down some sticky notes with how much water do you think we're going to do, and you can go back and look at your notes from the research on the types of tests, and somebody go ahead and put down for different tests what we're going to need. So Matter of fact, I could even do pH test needs. And then if I do that, can I change the text size? Normal caption. Yeah. So that would be like 1. And you guys can just pH test, BOD test. What were some of the others? Those were biological tests and a physical test, suspended solids. That was another one that I remember seeing on there. COD was another one that I saw on there. You guys have some of those numbers that you can just click on there and put some of the numbers in for how many cubic inches we need. Anybody looking it up vigorously right now? This is the hard part, right? I asked a question. It's like, okay, who's got that handy? Okay, so you might not have it handy, but have any of you ever done a pH test? This is sample volume needs. So the pH test, that just takes drops of water on a wick. A BOD test takes probably about probably about 20 milliliters per test. And so that's not very much. That's probably less than, probably about 0.5 cubic inch per test. Suspended solids is about the same, about 0.5 cubic inch. And a COD takes about 0.5 cubic inch. So if we're going to take a sample from a part in the river and we want to make sure that we have enough water from there, how much are we going to need? Somebody give me a thing with a total. Yeah. So Haley is saying, isn't it just a small amount for the test paper to dip it in? And that is correct. Or you use a dropper to put on it. Okay. So let's ask the next question. If I get my little sample of water and I'm going to do a couple of drops and I'm going to do this test and I'm going to do this test and I'm going to do this test. So we need about 1.5 cubic inch. How many samples do I need to run? Just if any of you have had, done these types of things or run tests before, do I just put one wick on and say that's good? How many samples, how many actual physical tests would we run on each of these? Like, let's say I've got a drop of water on a pH test strip. How many of those would I do? 5, 10, 100, 1,000? To make sure that from that spot, I just ran a good test. Anybody got kind of an idea on that? And you can pipe in on audio or type it in. Well, 5. That's a good number, actually. If you have an even number, it's hard to find, quote, the median, which is in between all of the samples. So Haley, why don't you go ahead and put down, we need 5 of each of these. Go ahead and put that on a sticky note or type it in on here. Go into the board and type it in with a sticky note and say we need 5 times this much. So we need about 5 times. with 7.5, probably 10 cubic inches is sort of what I'm guessing. So if somebody could put a sticky note on there, says, 5 samples each, that makes about 7.5 to 10 cubic inches. So now I'll ask the next question and put your initials on it. Put your initials at the front. Put an HD or something like that. So the next one is if I'm 10 feet deep. So here I am. I just ran a sample and I go to a new spot and the pump plus the tube is filled with my old sample of water. So we call the next thing the purge volume. So if I'm 10 feet deep with a 3/8 inch pipe going up to my sampler, my bucket up on my boat, 3/8 inch pipe, 10 feet deep, how much do I have to purge for 10 feet? Okay, so I'm going to put another one in here. I'm going to write purge volume. Three-eighths pipe by 10 feet. 3/8 pipe by 20 feet. And then there might be value in going deeper than that. Did anybody get a chance to look up how deep Sacramento River is and how deep you might want to go? I think 20 to 30 feet would be the max. So let's do one more. So somebody go and type in the volumes there. 3/8 pipe. And that should just be off of, so somebody go in and just give me those purge volumes. 30, okay, so good. So we know that it's 30 feet at the deepest point. I'm going to actually put this one right over next to this. And so this would be sort of like the minimum, and this would be like the maximum. Somebody get those calculations in there for me. Anybody got their calculator ready? This would just be on that Excel spreadsheet. Somebody pop that out for me as soon as you can. There we go. Thank you. That's really cool. So we're going to need, let's say, 3.2 cubic inches plus where was the other one? 10 cube. So we're going to have to do 15 cubic inches. 15 cubic inches. So how long is it going to take me? How fast do we have to pump? What do you think? How long do I want to sit there trying to get that purge done? What's a good amount of time? So now I'm going to type in there to purge and to pump for the test. What's a good amount of time, do you think? Now this one is purely like we have nothing to go by. Do you think 5 minutes, 10 minutes? There is a little bit to go by, but somebody just pop in. You can just put this one on the chat line if you want. What do you think? If we purge and test for about 10 minutes, 3 to 5 minutes, that'd be pretty good. Any idea how many of these locations we might want to do? I don't think that's too fast, actually. Let's say I'm going to do this in 4 places across at 4 depths so that I can really understand what it's like as that water is flowing through. That would be 15 to 20 times. So if I took 10 minutes, that would be 200. I'd be out there for 3 hours running my test. So even at 3 to 5 minutes would be sort of an hour and a half. So I like suggests 5 minutes times, I'm going to say 15 test locations is 150 minutes. So that's 150 minutes is, 16 tests if you do it. So this would be over 2 hours. And I'll say max there. So we're really saying probably we want to size the, now, the way this one is sized, how much do we get on each stroke? On each stroke, let's say the stroke is 2 inches. I think this is a 2.5-inch pipe, and you can't pull it at the end because then it might pop out the end. So how much water can I get per stroke on this?
What was the question?
So with the design as it stands right now, I think this is a 1/2-inch pipe, and my stroke I think is 2 inches. What's my volume per stroke in cubic inches? Oh, Mohammed says it's 0.5. Okay, so how many to get this done, to get the purge plus my sample. Purge plus sample in 5 minutes. How many times do I have to stroke that? Get sample plus purge in 5 minutes. That's what I'm really trying to get at here. And that's going to help us figure out whether this is an okay size or if we might want to look at making it bigger later on. So we've talked about how deep it is. We're working still on how to do this. But I need this answer now. How many strokes to get the sample plus the purge in 5 minutes? Because that's going to put us out on the river for a little over 2 hours. But then if we want to cut it down, we'll know what to do, right? Anybody got that one yet? Let's see. Let's see if I can figure it out here. Just see if I can get it. I've got 0.5 each times it strokes. Okay, and so I need to get 10 plus 5, 10 plus 3. So I need to get 13, and each time I do 0.5. So I need 26 strokes per 5 minutes. Oops. So I've got 26 strokes in 5 minutes. I got 5 strokes every minute, 5.2 strokes per minute. Does that sound reasonable? Yeah, so I just came up with 5.2. Let's see if I did that right. I need to get 13 cubic inches, and I get 0.5 per, so divided by 0.5. I need 26 strokes per 5 minutes. 5.2 strokes per minute. So that's like 10. That doesn't sound like it's that much, does it? That sounds like it's at least reasonable. Now, if I went with a bigger pipe size, of course, I could go slower. Yeah, so Haley is saying that's about 12 seconds per stroke. Make a couple of these a little smaller. Okay. So now that's just information. Well, let's talk about the next thing. So we've talked about that. How do we make the piston go in and out? If this is 30 feet underwater, and it's on an ROV, how do we make it go in and out? This is just done by hand right now. Anybody got good ideas? Some of you were looking at how do we make this thing drive and stuff like that. How do we make this piston go in and out? Anybody put any thought to that one yet? Something. I mean, so there's a few things to talk about here, right? So, what do you guys think? If you want to run a diaphragm, could be used, but how do you make the diaphragm go back and forth then? Something still has to push it. But yeah, a diaphragm could certainly be easier because then you don't have any force from the O-ring and you don't have problems with this growing, thermal expansion. But how do you push that? There's got to be some sort of a force that pushes it. What's going to push on it and what's going to pull on it or push back on it? An air pump. Yeah, air pump. And what will the air pump do? It'll pump air into this area and push it down, but what's going to push it back? Or pull it back? So I like that. So Haley says, we can definitely do that. Would an air pump be able to get the air underwater? Yeah. And then Haley says suction is an option, and that's true, but you can only suck so hard and times this area. But it could work. But the spring is also a good idea. So this one could be that. And you could So now what you'll see is now you've got something to go by. When you size your spring, you know kind of how long it'll have to be. If you go with this size, you go with a bigger diameter, it needs less pressure to develop the force. And a diaphragm is easier to push back, but a diaphragm doesn't have as much stroke length. A diaphragm can only stretch a little bit. So a diaphragm would have to have a big diameter and a small stroke length. A piston would have a small diameter and a big stroke length. So let's write that down. Piston, small diameter, long stroke. And diaphragm, big diameter, small stroke. And there's nothing wrong with either one. It's just, how do you want to do the design? Both ways work, but you have to use the design appropriately. Now, a spring with a big wide diameter is easier to fit in there. So maybe a spring to push the diaphragm back up would be easier, but now you've got a big diameter. Do you see any problem with putting a 3 or a 4-inch diameter tube on here? Anybody? What's this distance already? It's 5 inches from here to here. So if I put a 3-inch diameter on here, is it going to cause a problem? Anybody have an idea as to whether one of these is invalid because of space? Could be too big for the ROV claw, but that's a good point. So so that's a valid point to think about. My guess would be that the big round thing would sit on top here, and that you could extend this block underneath it and grab the block. Like right now, it would make sense to grab this with the claw or grab some part of the block where you could get on it. Like this is sitting right in the center of the block. Why? So now let's talk about that. So how will we make the piston? So you've got some ideas here. As you think about your design concept, in the end, you can think about that. You can think about that. Is there enough purchase to grip? Well, right now, you only have a small amount. If anybody wants to get in there and measure, you could do so. But this is dead center in it. Does it need to be dead center? Okay. Is there any reason for these holes to be in the center of this block? I'm going to suggest no. So do you guys agree with that? That this could be off center so that there's more room to grab, right? If we're using on this stuff. So if there's enough room, if you think there's enough room. Oh, okay. And so sorry, I missed Michelle's. Something like a crank or a circular wheel. And that's good. So I like that. I'm going to put that in there. But how do we make that crank go underwater? Do you have an idea on how you could make the crank or the wheel go underwater? So I'm going to add on because at some point we're going to talk about where physically is this. Okay. So there's a whole nother thing that this could be above the water, and instead of the tube being attached to the outlet, could the tube be attached to the inlet and just have the inlet down in the water? So if that's the case, I'm just going to put that here. If that's the case, is this circular crank or wheel any kind of a problem? Well, so Haley says that might remove the need for the ROV. Or do we need? That's an excellent question. An excellent question. Do we need good placement? Well, in the Sacramento River, it could be a problem. It could be a problem. There's a pretty good current and things are running down all the time, and it could be a problem. And you might need the ROV to take the inlet check down below. It's possible. I think that that's a question mark, and it certainly could make it easier to do. Okay. I think there are times when, especially when you're doing your first sample run across, where you would really want to know where that thing is. And so it could be that at times it needs to be below and times it needs to be above. But that's a great question to ask our marketing folks. Okay. And so now our last question is, what if something clogs it? And Wasan has already said, could you put a cage around it, around that? And you could. Let's see. So Michelle, then, if you're trying to keep the piston components out, would it be reasonable to offset the inlet and the outlets further down? Yes. And that's the other thing is this whole thing could be below, and this could be the only part that's above, right? I mean, so now all of a sudden you've got like 5 or 6 ways that you could envision this thing. Totally you could. And a mechanical component up above may have some advantages to the other one down, to having stuff down below. Although air is a great way to transmit energy. So what happens if something clogs it? Wasan is absolutely correct. And by the way, there's a whole nother way you could do this where this is down below and this just feeds into a big container right here, a bottle. And you bring it up, take the bottle off, send it back down. And that way you don't have so much of this purge problem. you have very little to purge, right? So you can actually have a bottle here that this just feeds into. Take it up, switch out the bottle, and away you go. And you're off to your next spot. So now you're seeing that there's lots of ways to do this. What happens if something clogs it? The longer it's underwater, the more chance there is to clog it. And yes, I would say you're going to need some sort of a cage or a screen. And as soon as the cage or screen is clogged, what do? Anybody got an idea? Anybody had a water softener or anything like that? What happens when that water softener gets plugged full of stuff? What do? Anybody know? You basically blow the gunk off with back pressure. So if you've got air here and you got a little valve right here, you could use that air to back blow everything off of the cage. Poof. It blows everything off. Okay. And so that's something that you might think about doing. But yes, it needs to be a cage. Replace the filter or reverse the flow. Yep. So there we go. So Alex says you either replace the filter or reverse the flow. So now if you're pulling this up after every one, you could obviously just put a new filter on and throw it back down. And while it's down there, you could do your other stuff. Okay. So now we're starting to really talk about how does it get past the check. Well, it doesn't. The cage would be out here, and it would have small, hopefully, and you can, by the way, make filters that are sort of self-cleaning. You can make self-cleaning filters so that just the flow of the water past it helps clean gunk off of it.
I guess I was just confused how reversing the flow, like how it would work with the different ball checks.
Okay, so it would be at okay, gotcha. So in that case, your ball check has a certain amount of pressure it takes to open it up that's made by this suction, and you would have a low pressure back charge on it. The other way you could do it, of course, is something like this, where you've got a ball, a pipe, and you only have perforations on one side of the pipe, and the water's flowing this way. So the water flows up and around it like that. So your filter would be less likely to clog because it's solid over here where things are hitting it, and it's on the back side, and you can still pull water in. So that's probably the easiest way to do it where you don't need to back pressure it. Okay. Woo, so we took a ton of time on operational functionality. Let's look at ease of manufacture. Okay. So could we replace these nipples right here? This one and this one. Basically with just a stub that sticks out and just thread it directly. Is that something that could be done? Okay, and Muhammad says you could replace 3 parts, 1, 2, 3, just by tapping this part, right? So I'm going to move Muhammad's over there. So that makes sense. Ease of manufacturing. What if I wanted to replace all of this stuff and put my own little ball check in there? It's essentially just a check, a ball, and a spring. That's all there is to it, is a ball and a spring. How about that? What if I wanted to do that? So might not need to have the 2-inch thickness. So really we're talking about, can we replace a lot of this stuff? I think the easiest one is this one where, like, why are we doing all this work? If I'm going to use a 1/2 inch pipe there, why not just make that a 1/2 inch hole? Right? So that one's kind of a no-brainer. It gets rid of a bunch of parts right here. This one goes right in. This one, I could probably, but that would just be getting rid of one part. So this is the one where we've got the most easy way to get a fix. Tap that hole direct. Replacing that with a stub is not too bad, but then I still have to thread it and put that on. So those are some things. But look, here's a big question. What if I want to change this and put a big diaphragm on there? Or I have another test to run and I have to put a bigger piston on here. What's the easiest way to make this time and time again so I only have to change one thing if I change my my functional requirement? What if I do different stuff? What if I change these tests and need to do something different? Is there value in having this 1/4 inch, 1/4 inch, 1/4 inch, not on just the one, but always making this and this and this exactly the same, no matter how I change that? Is there value in that? And how much is it going to cost me? So anybody got an estimate? So here's what I want to know next. What's the total cost of the purchased parts for this thing? Anybody got that for me? A check, a nipple, a bushing, a coupler, and a pipe nipple. And we won't worry about the O-ring right now. Anybody got that cost? Somebody's got to have it added up. Let's just do a quick estimate while you guys are working, while somebody is getting it for me. I think it's like these nipples are like $2 a piece, so 2 times 2. And these check assemblies are like $4 a piece, plus 2 times 4. Oh, that didn't work. 4 plus 8. The bushing was about 6. Coupler was about 5. And that other nipple was about 3. Anybody got the number? 13 to 63, depending on what we do, right? Okay. And so I'm going to say it's about $25. There we go. Cool. So there we go. So if that's even better. So if it's, I'm going to make that big again so we can see it. So if we use 3/16 stainless steel, it's 63. If we use brass or PVC, and the cheapest is 13. Okay, perfect. Okay, so these fittings and these parts. So that gives us some information. Okay. Now, how much does it cost us to screw a bunch of pieces together? Not much. It took me about 5 minutes to put it together. So that's not too bad. So that cost isn't a lot. So here's the really key one right here. When we start looking at our materials and we start figuring out corrosion and things like that, $63 to $13. Really, it's not the size of my design that's going to make the big difference. It's my material selection. Now, let's take a look. If I make this block out of 316 stainless steel, it's pretty hard to machine versus just a chunk of brass or bronze. And you can't get a chunk of PVC, but we could get a chunk of some sort of plastic that we could use. So machining wise, it's not too hard to put a hole through, and it's not too hard to change the size of my drill to put this hole through. So I don't think that I've got too much if I'm making all these parts or buying all these parts. What's expensive is if I want to have this stub sticking out and I thread it. That would be expensive. Or if I have this stub sticking out and I thread it. So I think this concept of just punching the holes through and threading them at whatever size your design is probably the cheapest. And I'm looking at it, and my total cost, even if I go with 316 stainless steel all the way around, is going to be about $63. Okay? So that's what we're looking at for that. And I'm going to put just really quickly. Just so we know who made this comment right there. Okay, and that was Wasan's comment. Can we get this attached directly to the block? So now let's talk about Michelle's. If we don't have the 2-inch thickness to grab onto, and you're right, what if we made this out of a piece of plate, put a hole here and a hole here, and let's say we made that 1/2 inch. And we still made this stick out a way for the claw to grab onto. Okay, so that might be a way that you could think of. Instead of a 2 by 2 by 2, you might get away with a 1/2 inch or a 3/4 by not even 2, right? It didn't even have to be 2. Maybe it's 1 by 2. So Michelle's idea of saving on the material. Now, if it's 3D printed, we don't save on material, but we save on time. But if you're going to make this out of an aluminum block or a 316 or a brass block, you're going to save a significant amount. And I'll leave it up to you to look that up to find out how much you might save if you were to do something like this, where the claw grabs here and you've got these holes, and they're centered up on this side and on this side, but this dimension is just enough to give you room to get your hole, the depth of your tap, and the depth of your tap. That would significantly change the cost. Okay, now adding a hole or a lightning thing in here would not do very much for us because we still have to buy the material, and then I have to cut the hole. Okay, but a little wafer would be really a good idea. I like this concept here that Michelle brought up. I like this concept that Wasan brought up. And these numbers here really tell us about, now, how cheap does this have to be? Okay, if you want it to last forever, you can do this. But if you want to sell a very inexpensive one and let other people do the testing. And hey, if it breaks, you can buy 5 of them for the price of that one. So maybe that's a good thing. That's going to be up to you. We have only a few minutes left, but ease of maintenance. Okay, so the power, we talked about that a little bit. Jan says that 316 would be great corrosion resistance all the way through, and it certainly would, but you would have some expense. And you might think about, if you're going to charge somebody to go out and do all this, how many tests do you need to run before the cost of this is a very small amount of each test? Let's say you were able to do 10 tests per week throughout the Sacramento area, and you charged, for the battery of tests, you charged $300. Then each time you went out, 10 tests, you'd probably pay this back if you added $2 per test, 1%. You'd pay that back in some significant amount of time. And as you're talking about how to make this and looking at a cost, which we will actually do later, we would look at that. So that's a good thing. And how expensive is it? It depends on how many times you want to use it before you've paid for your expense to make it. Okay? And so which parts are disposable? If this is just, literally, I could make this from a PVC cross. I could just, all of this could be a PVC cross, and then I just add that and that. And I could throw this away after a certain point, not even worry about sterilizing it. If sterilizing it cost me $10 and the whole thing cost me $8 or $9, maybe I just want to take these parts off and reuse this part and just throw this part away. Now, that's not very good from the point of view of our environment, for sure. Okay? But when you sterilize something, you usually use hot water or acid. So I'm going to let you know that. That was my job for years in the wastewater treatment plant, cleaning things with hot water and acid. So you would want to do a quick check of these materials and not just look at corrosion, but look at cleaning them. Which ones can handle hot water and acid? And see if the plastic that's being used can handle those and things like that. Corrosion resistance, size stability. If this thing gets cold, it's going to grip down on these threads, and I don't think it'll be a problem. But what if you take it back and it gets hot? The big problem is, what do you make all this stuff out of? Size stability. So I'd like somebody, if you've got this part and it changes 60 degrees, oh, there it is. So there's our thermal expansions. And that's inches per inch. So let's see. 10 to the minus 6. Okay, so here we go. Here comes my calculator again. That's about 0.5 across. So it's 0.5 inches times 0.12345 6 times 60 degrees. Well, that's not changing very much. So, oh, that's the naval brass. PVC is 28. Does anybody remember what I had down for PLA? What this is made out of? So we can redo that. I think PLA was like 65. So 0.5 times 0.0, oops, 0.12345. That's 10 to the minus 6 times 60. About 2 thousandths of an inch. Will 2 thousandths of an inch change make that thing seal better or worse? Or become too hard to push or pull? Somebody look up those limits on the on an O-ring. What was kind of the range for the O-ring? Okay, I think that these are all like plus or minus 1 thousandths of an inch. It was like they gave 2 or 3 thousandths. So this is right at the edge of possible, but we might want to make this out of one of these materials. So I'm going to put this up here and say that making that piston out of plastic might be a bad idea, but making it out of stainless steel or one of these alloys, minus 68, hot water, okay, 140. Okay, so that's good. Cool. That's interesting. Okay, so we've got some stuff. Pasted a chart. There we go. Thank you. So you pasted one, but it's not showing up either. Which one? Maybe you got it pasted over on one of these. Now, I don't know where that's going. Oh, there it is. I found it. Cool. It was just in a funny spot. It went up on a different one. I don't know how to move it over to a different one. But it's on a different one. I don't know how to move it to a different one. That's okay. Let's go to this last one because we're almost done. We're going to go just a few minutes over time. And you can just think about these ones. Okay, so Michelle has posted some information. And what happens if one of these connections breaks underwater? Okay, so if the piston breaks, what would happen? Now, there's likely, because what we were talking about, if it's underwater, it's going to be attached by an air tube. So it'll break, but, who knows? It just won't work anymore. And if one of these breaks, one will be attached to some tube and it'll just be floating out, but one of them will be a problem. So if one of the connections breaks, though, it's definitely going to stop working. But that's probably all, right? What else will happen? There we go. There. Oh, it does go like that. There we go. So what else would happen? If it breaks or if it fouls, what happens? What's the failure mode? Is it, it stopped and I got to replace something? Is it, something bad is going to happen, I'm going to make a mess and fix it and pick it up, or is it just I just have to fix the pump? What's going to happen if something breaks or if it fouls? Somebody post something on there. How bad is it? I'm going to write this. So you can have a total environmental disaster. Tests are done for the day. Ruins all of the tests so far. These are things that I could think of that if something happens. So which one of those is it, right? You'll want to think about that. So it's not a total environmental disaster. Maybe tests are done for the day. It certainly doesn't ruin all the tests. Or maybe, yeah, a backup pump. Have a backup pump if something fails. Who put that? Would be sure to put your initials on there. Okay. So yeah. So now we're going to talk, and we don't really know, but it's likely something's going to break whenever you go out there. So you might go out there with 2 or 3 of these things. So you might sell these in a set of 5. So now we're going to start talking about, okay, and when something breaks, what are you going to do with the broken parts? Do you throw them away? Do you get to rework them? Do you just clean them and reassemble it again? I want you to think about those things. When you're out there, you're just going to slap a new pump on the ROV and get it down and going again. Okay? But then you're going to have this box of maybe broken parts, and you have to think about what to do with them. Do you want to take them back and repair them? Do you want to just throw them away because it's cheaper to buy a whole new one? Do you want to try to reassemble it right then and there? Okay. And then the big question is, what are you really selling? Okay. And Wasan, you're going to have to pay attention to this because you're going to be building our facility, right? Yeah, repair it with a new part. Okay, so maybe instead of having a backup pump, you've got a bunch of backup parts. That might be the way to go. But that might take a little while, so you don't know. But what is your business really going to be? We haven't really talked about that. But as you talk about developing your version of this design, you're going to want to be able to address your vision for this. Okay? Are we trying to sell pumps and we're doing a test service so that people can go out and do their own stuff and send us the results, and we have this lab and we give them the results and post them and make money that way, and we have to sell pumps to do that? Are we selling the service? We're going to go out and do it and unload the difficulty off of the clients and just post it. Or are we going to just post test results? Okay. Most of these test results, they can just transmit the test results to us and we'll report them, but we're giving them the equipment to work with. So, or is it all 3 of these? So as you are doing your last slide of the presentation, not of the design review, is the last slide of the presentation, we'll want you to think about these last things and do it. So here's my last little bit, and I know we're a little bit over time. Does anybody have a question about left that they still need to answer to come up with some suggestions of why we keep this design exactly like it is or what we might do to fix it or make it better. Okay, nobody's jumping in right away. So let me just show you. On the last slide of your presentation, you're supposed to make some suggestions. And if your sketch is as simple as something like this with some arrows at it, just think of Design 320 and your initial sketches. You can do it in SketchUp or in Inventor or whatever you want, but you've got all these files that you can play with. Okay. And if you want to put a diaphragm up there and talk, you can go look at those things. I think a diaphragm could be an excellent idea for this. As a matter of fact, you wouldn't even need the piston anymore. You just push on it with some air, and you could probably find a spring that is the right size. But you have to look and see, right? And you have to give some numbers of why it might be good. But this is as simple as your new design might be with some notes. So your job now, thank you all for being part of this design review. Hopefully you've learned a little bit about what a design review is like and how you might be prepared and have numbers for us to look at, that we can calculate with and put real things on here so that we can understand the value of certain things and just make some decisions. Okay? So now you get to put your own chief engineer hat on and go to the last page of the presentation and make a suggestion. Tomorrow, we'll look at a few other things, the milling machine and stuff, but literally what you're going to do is put that and maybe a few more notes on each page of your presentation and maybe just circle the part that was yours. Like Michelle can circle that one and that one just to identify that that was the input. The last thing I'm going to do here is post this. Let's see if this works. Didn't, oh, it did. There we go. So that is your recording also of what people input. Okay? So you've got that too, and you can look through here to also point out where you were giving your input. Okay. Last questions? All right, I'm going to stop the recording.